I would like to demonstrate the effect of curvature on charge density on an object. So here I have an aluminum pot. So if I put some charge on it, it would be sitting here and it would be an equipotential. The voltage would be the same everywhere. And so what we'll see is that the density of charge along this surface here with the slow curvature will be less than the density of charge, say, on the handle here. And correspondingly, the electric field emanating from this region will be smaller than the electric field emanating from this region, because we know that the electric flux density will be everywhere normal and equal to the charge density on the surface. Okay, so I've found a use for our textbook to isolate our conducting aluminum pot here, and I'm going to use the electrophorus to charge it up. So quite a few times I'm going to repeatedly put charge on it using the electrophorus here. So now I want to sample the charge on the slow curvature outer part of the pot here, and then also on the sharper, faster curvature of the handle. And I'm going to use something called a proof plane. Now this is a small metal plane supported by an insulating handle and used to transfer a small fraction of the electric charge on a body to the electroscope. So I fastened one here out of a piece of glass, that's the insulator, and just crudely by folding up and attaching some aluminum foil. So what I'm going to do is touch the outer part here and then the electroscope. So when I touch the outer part, this small area will sample some of the charge on this region, and then I'll transfer it to the electroscope to see how much I have on the aluminum foil here. And then I will reset the electroscope and do the same thing by touching the handle here to sample the charge on the handle. Okay, so I touched the proof plane to the slow curvature outer part of the pot, and now I touch my electroscope. And there's a slight deflection as I transfer the charge from this side of the pot to the electroscope. So let me reset the electroscope. Now let me touch this higher curvature handle, and now let me touch the electroscope. So you can see I transferred a much larger amount of charge from the handle than from this outer slower curving part of the pot. So we know the pot is an equipotential surface, so between any 2 points the voltage is 0, but clearly there's a much lower charge density on this slow curving outer wall than on this much sharper curving handle. Here we have an object with 3 different curvatures. So the greatest curvature is on the right hand end, then the left hand end, and finally the sides with the least curvature here. Now if we go and put some charge on the object, it will redistribute until it is at an equipotential. And from the experiments we just did, we know that the charge density would look maybe something like this, with the greatest charge density here where we have the greatest curvature, then a little bit less charge density here where we have the slower curvature, and finally the least amount of charge density on these two ends here. And we know that the electric flux density lines will come out normal to the surface because this object is an equipotential object. Okay, so now let's take 2 spheres out of this object like this. Okay, so let's cut these 2 spheres out, and then let's start separating them, but let's maintain contact with a wire here. And we're going to separate them to a large distance so that eventually we'll have the following situation. Okay, so we'll have these 2 spheres. We've maintained contact with this wire, so they've remained at an equipotential, and at this point they're separated by a great distance. This one we'll call sphere 2 with radius r sub 2, total charge on it q sub 2, and the charge density on the surface rho sub s2, and this will be sphere 1 with radius, charge, and charge density defined as shown. The potential difference between this object and infinity is how much work it takes to bring 1 coulomb of charge from infinity to the object. Now, for convenience, we like to set the potential at infinity as 0, so then we can think of the potential of these objects as being just the amount of work it takes to bring 1 coulomb of charge from infinity to the object. Now, we've separated sphere 2 and sphere 1 by a great distance, so the amount of work it would take to bring a charge from infinity to sphere 2 is going to be independent of sphere 1 because it's so far away. Similarly, the amount of work it takes to bring a 1 coulomb charge from infinity to sphere 1 is going to be independent of sphere 2 because sphere 2 is so far away. But because they're connected by a wire, the potential we will get will be the same. Okay, so the potential we know then for a sphere with a charge on it is equal to 1 over 4 pi epsilon sub 0 times the charge on the sphere divided by the radius of the sphere. And so the two are going to be equal. Now, if we solve for Q1 over Q2, we see that it's equal to the radius of R1 to R2. So sphere 2 will have a larger amount of charge on it than sphere 1 by the ratio of the radii of the two spheres. Okay, now the surface area of a sphere is 4 pi r squared. So the charge density is just the total charge divided by 4 pi r squared. Okay, so here we have the charge density on the two spheres. So if we divide the charge density on sphere 1 by the charge density on sphere 2, it's going to be equal to Q1 over Q2 times r sub 2 squared over r sub 1 squared. But we've already found that the ratio of the charge on Q1 to Q2 is R1 over R2, so the ratio of the charge densities is just the ratio of the radii of the two spheres. So here we clearly see that the charge density will depend on the radius of the curvature at that point on our object. Let's assume the radius of sphere 1 here is 1 meter and the radius of sphere 2 is 5 meters. So we've just developed an equation on how the charge densities on the two spheres compared to the radii of the two spheres. So the charge density on sphere 1 is going to equal R2 over R1 times the charge density on sphere 2. So for this particular example, the charge density on our smaller 1 meter sphere is going to be 5 times the charge density on our 5 meter sphere.